So we should say, okay, so let's let A and B be elements of the kernel, right? And let's let R be in the ring. We're gonna apply that. I erased it, but the test I wrote up for you a second ago, the ideal test, you know. So first of all, how about A minus B? Is it in there? Well, number one, consider. But what is it? They're not 0. How about phi of A minus B? What's that equal to? We don't get to say A and B are 0. We get to, what we know is that phi of A is equal to 0 and phi of B is equal to 0.
But we have that thing, number 1.
Okay, yeah, very good. So a consequence of that is this, right? I haven't proved that, but you can prove that.
Can you just say it's n r minus 1r?
Yes, yes.
There we go. So 0 minus 0.
0 minus 0. So therefore, A minus B is in the kernel. To get into the kernel, you have to map to 0 under phi.
Okay.
That's the definition of kernel. So what about phi of, AR? Well, phi A, phi R, which is 0 times phi R, which is 0. And likewise, phi of RA is phi R times phi A, which is phi R times 0, which is 0. So therefore, AR is in the kernel, and RA is in the kernel. So what else do we need? We need that it's a subset of the ring. That's clear already. So therefore, the kernel of phi is an ideal of R. All right? Now that in isolation doesn't maybe seem like much, but when you pair it with the next theorem, it's actually really powerful in terms of its constructive use, because theorem 4.47, it's therefore kernel ideal. Kernel of phi is an ideal of R. We don't have to say sub, like kernel's already, ideal is already kind of a sub-object. We don't have to, so theorem 4.47 says take a ring homomorphism, R to S ring homomorphism, right? Then the mapping from R mod the kernel to phi of R by the rule R plus kernel, phi maps to phi of R, is a ring isomorphism. In other words, let me put it in other terms. We have the result that R mod the kernel of phi is isomorphic to the image of the ring homomorphism. This is the first isomorphism theorem for rings. You guys talk about the first isomorphism theorem for groups? Yeah, this is it for rings. And it's basically working off the additive group that's sitting inside the ring, right? It's really mostly the additive, it's mostly the first isomorphism theorem for the additive group sitting inside the ring. Just, the multiplicative stuff does ride along nicely, as you'd hope. Yeah, that's what you finished on. Cool. I left the proof as an exercise for the reader. The main thing to prove here is that mapping is, an an isomorphism. And, oh, good. And also, of course, that it is bijective map, you know. And basically what that boils down to is for that map to be one-to-one, you know, if you have two different things like, you know, phi of R1 plus kernel phi, and R2 plus kernel phi both mapping to such that phi of R1 equals to phi of R2, well, then that means that phi of R1 minus R2 is equal to 0, which means that R1 minus R2 is in the kernel, which then means that R1 plus kernel plus equals to R2 plus kernel, which it goes back to show you that, like, equality of outputs implies equality of inputs, which is to say that it's one-to-one. And it's already surjective, essentially, by assumption, right? Because, like, this, you pick anything in the image of R, well, R plus this maps to it. So it's like almost automatically surjective. So then the question is, you know, can you prove that that map satisfies, preserves the operations of addition and multiplication? And that's pretty straightforward. But there's more. But there's more. Like, there's always more. 4.48, it says that every ideal of a ring R is the kernel of a ring homomorphism. Right? In particular, you might say, well, what is that one? Well, the mapping R maps to R plus A from R to R mod A takes, and we call this mapping psi, kernel psi equals to A. So that's theorem 4.48. So I'll let you look at the proof of that is not especially difficult. I'll let you read it. I think we'll end with a couple of examples here. All right. Here we have phi going from polynomials and the integers to the integers. And I'm defining it, this is the evaluation morphism actually. Phi of f of x equals to f of 0. All right. So I say since phi is a surjective ring homomorphism, do you agree? Is phi surjective? Is phi surjective?
That's onto, right?
Onto, yeah. So let's prove it. Let A be an element of the integers. Then phi of what? I mean, you could do anything you like. Like, here's one that'll make you feel better. How about x plus a? Phi of x plus a is equal to what? 0 plus a, which is equal to a, right? Make you feel like we did something. Put x equal to 0. I could just as well write a there and say phi of a equals to a, because when you evaluate the constant polynomial, you just get back. Like, how do you constant polynomial is 3. Evaluate 3 at pi. 3. This is very disconcerting to calculus students, but true. So I put an x there to make you guys feel like we did something, you know? Okay, so A is arbitrary, therefore, yes, phi is surjective, right? Because we just showed that you can map to anything, any integer. What's the kernel of this map? What's the kernel of phi? Well, let's write it out. That's f of x in zx such that what? F of 0 equal to, I mean, this is phi of f of x, right? Phi of f of x is f of 0, right? I'll write it out. Phi of f of x equals to f of 0 equals to 0. What do you guys know from algebra? The factor theorem, right? What does it mean for a polynomial to have 0 mapped to 0? That means that x is a factor of the polynomial, right? So this is precisely this, right? It's things that have x as a factor, right? This is so then what? So first isomorphism theorem, what's it say? It says that if we take z of x and we quotient by the kernel, which is this, right? We get the phi, right? The phi of z x, right? The image, right? But we just proved it's surjective, right? So this is z. So we have the kind of neat result that if you take polynomials over x and you quotient by the ideal generated by x, you get back up to isomorphism z again, which squares well with our intuition that when you look at the factor ring generated by x, what you're doing is you're making x equal to 0. So multiples of x are equal to 0, right? So if you have a polynomial, you know, a plus bx plus cx squared plus da-da-da-da plus, you know, cn x to the n plus the ideal generated by x, well, that's just equal to a plus the ideal generated by x, right? Because in this ideal, in this factor ring where x is the ideal, x plays the role of 0, right? So you can absorb powers of x and so forth into the ideal, and all that survives is a. But of course, this is just a really stupid notation for a, you know. So the isomorphism there is just to drop the x. You know. I mean, I can actually write down the literal isomorphism for you here. But anyway, that is an example of the first isomorphism theorem, which I think is good for us to go through. So that brings us to theorem 4.410, which I guess is where we'll pick up next time. So next time is very exciting. We'll talk about the concept of like the smallest field which fits inside a given field, and we'll explain that there's something called a prime subfield, which is like it's the subfield which is contained in all other subfields. It turns out the prime subfield is either the rational numbers or z mod p, where p is a prime, and then we'll show that. We'll go through the formal construction of rational numbers, the so-called field of fractions argument, which I think is like really one of the high points of this part of the course, like seeing how you can explicitly construct rational numbers from like rigorous mathematics. And that's in our construction, it's not just rational numbers, like it equally well applies to construct other quote-unquote fields of fractions, not just the rational numbers. So it's pretty neat. That's up next time. So thanks, guys.